Hey guys, I hope this video finds you well. We are about to start our last chapter. What? Yes, chapter 5. And the topics are rational functions as well as radical functions. But first, rationals. Okay, so I have an activity planned. This goes with the document provided. We're going to talk about rational functions as well as their vertical asymptotes. Yes, you heard that word correctly, asymptotes. So let me share my screen and we will get started on a couple of things. Okay, so first and foremost, this is the document that I have provided for you. And the very first thing we want to do is just get a feel for what these graphs look like. And we're going to fill in these table of values together and talk about some characteristics and vocab as we go. So let's start with pulling up a Desmos for this. Okay, so if you would play along with me here and pull up a Desmos either on your computer or on your phone, whatever, and type in just the first function, f of x equals 5 over the quantity x minus 2, and it should produce a graph that looks like mine. And as you can see, there appears to be two very distinct portions to this graph, and we are going to talk about today why that's the case and what's happening as to why this graph appears to be broken up into two parts. So after you have your function typed in, what I want you to do is I want you to go up here to the little gear setting, and we're going to edit. And then by that function, whatever line that function is in, you're going to click the table feature. And what that should do is it should turn your formula, well, your formula is still there, obviously, but it will create another line underneath it that is a table for that formula. See how it says f of x? That tells me that it's using that same formula right there, f of x. Okay, but let's expand our table just a little bit. I want it to go from -3 all the way up to +3 or maybe even +4. But either way, let's get a nice broad, some negatives, some positives, a nice broad view of these table values. Okay, so as you can see, most of these table values just produced answers with the exception of plugging in 2. So we'll come back and we'll talk about that. But so when you plug in -3, that means it would be 5 divided by whatever -3 minus 2 is, and that's how it's getting that the answer is -1. It's just doing that math. When you plug in -2, then it would be 5 divided by -2 minus 2, and it's just getting that answer. So all of these table values are simply found by Desmos plugging in this number for x and spitting out whatever the answer would be. So you can see that when you plug in some negatives here, you get some negative answers. That's these dots. It's like this guy and that guy and this guy and that guy and this guy, right? So those are all those answers. Then you hit this weird one. We'll come back and talk about that. And then on the other side of it, you get more answers though. You plug in 3, you get 5. You plug in 4, you get 2.5. And we could expand this table even more if we wanted to. So it's producing all these different table values. As you can see, they are then populated onto the graph, producing an image that looks like this. But we can't plug in 2. Well, why can't we plug in 2? Let's ask ourselves this. I'm going to add just a new expression here. What would happen if we did plug in 2? It would say 5 divided by 2 minus 2. Now notice that does say undefined, so it's not possible. But why is it not possible? So think about this. What is 2 minus 2? 0. So when you plug in 2, what you're asking the formula to do is take 5 and divide it by 0. Well, ladies and gentlemen, that's not possible. You can't take 5 and divide it into no parts, divide it into no groups. How many times does 0 go into 5? I'm sorry, what? You can't even begin to talk about that. 5 divided by 0 is not possible. That's why it's not producing an answer. So my expectation so far is that you copy these table values, -3, -2, -1, 0, 1, 2, 3, 4. Copy those table values. Oops, not that. That's my own homework. Yes, folks, I have homework too. Remember, I'm a student right now. Where is that Word document? Oh, I know, it's not a Word document. It is, here we go. Okay, so copy those numbers into this table right here. So just like -2 right there, -1 right there, 0, 1, 2, 3. Okay, so just copy over those numbers and make sure that you have the number 2 in your table so that you can write down that it was indeed, you know, undefined. So make sure you have record of that. So just fill in that table. But now in this next little table on this side of the chart, okay, this side right here, I want us to plug in numbers that are really, really close to 2. Okay, fine. I can't plug in 2, but can I plug in, I'm going to delete my table so I can get some fresh numbers in here. I can't plug in 2, but can I plug in 1.9? Yes, I can. Can I plug in 1.99? Yes, I can. Can I plug in 1.999? Yes, yes, I can. All right, what about if I go on the other side of 2? Now again, I can't plug in 2 because 2 minus 2 is 0, and that would be an error. But can I plug in 2.01? Yes, I can. Can I plug in 2.001? Yep. How about 2.001? Oops, another, oh no, that's right. Nope, another one, extra 0. There we go, 2.0001. Yes, I can. So I want you to capture this message right here. The fact that just because I can't plug in 2, I can plug in numbers that are really close to 2. So you're going to record those values in this table right here. Okay, so why am I wanting you to look at that? Well, here's the scoop. If you go back to the graph, you'll notice that as you approach the number 2 on the x-axis, your graph just shoots either all the way down in like the downward direction towards -infinity. Notice my mouse right now, it says 1.88. That's because, yeah, I can plug in 1.88. I can plug in 1.926. I can plug in 1.95. And as I plug in those numbers, I get these really, really, really big, in this case negative, but nonetheless really big negative answers out of it. Now, if we go back to our home screen and look at the other side of things. So coming in from this direction, can I plug in 2? No, but can I plug in 2.6? Yeah. Can I plug in 2.3? Yeah. Can I plug in 2.174? Yeah. And so you'll notice on this side, as you get closer and closer and closer to that 2, you get these really, 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 really big answers. As long as, of course, you don't plug in exactly 2, because if you plug in exactly 2, well, once again, 2 minus 2 is 0, and that is not possible. So what your graph looks like is as you approach that sort of boundary, wherever that line of like imaginary impossible is, in this case, the impossible number is 2. So wherever that boundary is at 2, your graph is going to get really, really close to that on either side without ever touching it. And as far as the answers or the outputs go, they either shoot up towards positive infinity or down towards negative infinity, depending on what side of the graph you're looking at. So that's why I wanted you to have that other table in there to show that, okay, just because you can't plug in the number 2 doesn't mean you can't get really, really, really close to it. And notice you get really, really big answers as you get closer and closer and closer to that boundary. Again, when I say boundary, I mean the number that doesn't exist. You can't plug in 2 in this case. So 2 is your boundary. Now, graphically speaking, here would be my expectation. So when you graph this, the boundary, like I said, is at 2 in this case. And so you've got this invisible kind of boundary we like to indicate it with a dotted line, kind of like the axis of symmetry in our last chapter that we do dotted lines for it. So you've got this boundary at -2. And then other than that, we saw on Desmos that the graph lives kind of on this side in a swooping fashion. And then also on this side in a swooping fashion. Now notice how careful I'm being though to not actually intersect or run into, so to speak, that dotted line, because as you guys saw on Desmos, you cannot be equal to that dotted line. You cannot actually reach, oh dang it, it's +2, Shannon. Just kidding, just kidding. +2, oh darn it. I'm sorry guys, I don't know why I had -2 in my head. And I don't want to restart this video. So guess what? We're going to deal with it. Okay, let's redraw. +2. Oh my goodness. Okay, +2 was my boundary. +2, +2, +2. That's my boundary. That's my boundary. This guy was like over here. There we go. And this guy was like over there. Okay, much better. Sorry. All right. So notice when I drew my little curves though, I was really careful not to actually hit that dotted line because there is no graph. The graph does not exist at +2. It gets really close to it, yes, but it does not hit +2. So you have to be really careful when you draw these graphs to not accidentally, let me draw something that would be an incorrect answer. Ready? This, oops, this, friends, would be incorrect. Whee! See what I did there? Yeah, no, that's wrong. You can't have this curve go slicing right through the number 2 because after all, when I plug in 2, do I get an answer? No, I don't. So the graph does not go through that point. Okay, so you'll have to be careful when you draw these, and that's, by the way, why we indicate it with a dotted line. So if you cannot plug in +2 for this one, and again, why can I not plug in +2? Well, because 2 minus 2 is 0, and that would simply be impossible. Can you take a second and look at this next one and make a little prediction with me? What number do you think is going to cause the undefined error message in Desmos for this one? Think about it. What number, when you plug it in, would make that whole denominator become a big fat 0? 2 times what plus 6 makes 0? Think about it, think about it. Let's go to our Desmos. I'm gonna X out my old one, and here's my new one. Okay, feel free to type that in your Desmos. G of x equals -5 divided by the quantity 2x plus 6. You can already see on graph paper that once again, there's 2 branches. We call these branches. There's 2 sections to this graph. Notice they are broken apart again, but where are they broken apart? Let's hit this little wrench right here and do a table. And I'm going to expand my table again. -4, -3, -2, -1, 0, 1, 2, 3, okay. Where's the undefined message now? Ah, -3. You see it? Right there, -3. So how come -3 is the culprit? -5 divided by 2 times -3 plus 6. That is an error. Why is that an error? Oops, forgot my divided by symbol. Hang on, back up the trolley. -5 divided by, there we go, 2 times -3 plus 6. Okay, that is undefined. You cannot plug in -3. Why? Think about it. Guys, what's 2 times -3? -6. What's -6 plus 6? 0. And what's 5 divided by 0? Undefined, not possible. Okay, so on this particular formula or function, you are seeing that the breaking point that separates the curve is at -3. So once again, I expect you to have all of these table numbers written down on your document so that you have record that all these numbers, you plug them in, they work, they work, they work. Oh, but not this one. Okay. Well, similar as we did on the last one, I want you to see that just because you can't plug in -3 doesn't mean you can't plug in stuff that's really close to it. So after you get your table numbers typed in right here, then in this next chart, I want us to plug in numbers that are really close to -3. Can I plug in -3? No, I cannot. But can I plug in -2.99999? Well, let's see. So if I plug in -2.999, yeah, there's an answer for that. -2.9, yeah, there's an answer for that. -2.99999. Yes, there's an answer for that. What about on the other side of things? I can't plug in -3, but can I plug in, I don't know, -3.1? Yeah. Can I plug in -3.01? Yeah. Can I plug in -3.0001? Yeah. Okay, so you get my drift. Can you plug in -3? No, that would be an error. But can you plug in anything leading up to that point? Yes, you can. And notice when you plug in numbers really close to that breaking point, you get really big answers as your result. So you'll look at this graph with me and notice that on this side of the world, as I get closer and closer and closer to that -3 mark, my graph is shooting up towards infinity. It just goes up and up and up and up and up and up and up. Notice it never actually reaches the number -3. Nope. But it gets really close to -3. And on the other side, approaching from this direction, I'm swooping in from the right-hand side now, negative like 2.3, yep, I can plug in that. -2.8, yep, I can plug in that. -2.9, yes, I can plug in that. And you'll notice that on this one, it just shoots down, 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 down towards negative infinity as you get closer and closer and closer to that -3 mark. So back to our document. So on this one, what we found is that -3 is that breaking point, that error spot. So we're going to indicate that with a dotted line. And on this one, my two little branches, let me go back to my home screen. So they were in the upper left and lower right. Upper left, so up here, get really, really close, but don't actually touch it. And then on this side, they were over here. Get really, 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 really close, but don't actually touch it. Okay, very good. Okay, so that gives you a sense of what these graphs are looking like, and the fact that their domain, yes, we're going to go there next, the fact that their domain is definitely not all real numbers, guys. The fact that you have error messages tells us that we can't just say all real numbers, because obviously not everything works. So you'll have to always identify for your domain, okay, well, what doesn't work then? So let's go back up here. We said that for x -2, the value that caused the error was +2, right? And the reason why it's +2 is because 2 minus 2 is 0, and that's not allowed. You can't divide by 0. And then on this one, we said the error was at -3. And if you think about that, it's because 2 times -3 plus 6 is 0, and you can't divide by 0. So pretty much whatever number would make the bottoms of these denominators, whatever number would make the denominators of these be equal, come on, where's my little pen? Here we go. Equal to 0, that is the number that we care about. That's going to be the value that causes the error. So like for x -2, when does x -2 equal 0? At +2. So that's why my dotted line was drawn at positive 2. On this one, when does 2x plus 6 equal 0? Well, at negative, when x equals negative 3. That's when the error is on that one. So you'll always have to identify where that error point is. Okay, so now let's get some vocab. So on this little blank space down here in your document, okay, we're gonna type some good stuff. All right, so for some vocabulary, first of all, these functions are called rational functions. Can I make that bigger? Certainly I can. Let's see. There we go. Okay, so these functions are called rational functions. And what do we even mean by rational function? A rational function is simply the division or fraction of two functions. So like, for instance, if I give you a formula, it's going to have something on top, it's going to have a division bar in it, and it's going to have something on the bottom. Now, the letters g of x and h of x, guys, please, that's just totally arbitrary. Those are just function notation. That's just us using math talk because we're fancy, all right? Your main takeaway message is there will be something in the numerator position and something in the denominator position. Go back and look up here. I had a 5 on top and I had an x minus 2 on the bottom. Over here I had a negative 5 on top and I had a 2x plus 6 on the bottom. The main thing is that you're going to know something is a rational function because it's going to be the division of two things. I didn't want that whole thing bold. I just wanted the word division bold, but apparently that's not possible. So you're going to know that it's rational because there's a division bar in it. Guys, this is the first formula that we've had so far that was a division formula. So that's important. Now, since it's got a division bar in it though, as you guys saw, some errors happen. In mathematics, you can't divide by 0. Well, guys, if these formulas have division bars in it, you're going to always be worried about that. What if you're dividing by 0? You're going to get an error message. So that error message, ladies and gents, has its own vocab word. Ready? It's called the vertical asymptote. Okay, vertical asymptote vocab word is by definition the value of the input variable that causes an error. And when we say error, we mean division by 0. Division by 0. You cannot divide by 0. So wherever that value of the input is, we call that the vertical asymptote. So back up here, we said it happened when x equaled 2, right? Oops, I just wanted to draw a box. Can I draw a box? Yes, no, I just want to draw a box. Here we go. So we said that the value of x that caused the error was 2. Well, vocab word, guess what? The vertical asymptote is x equals 2. On this one, the value that caused my error was x equals negative 3. So guess what? The vertical asymptote is at negative 3. So you'll notice that it always comes from that denominator. Whenever the denominator equals 0, that's when you're going to have your vertical asymptote. Now, since you're going to have these vertical asymptotes, aka errors, the other thing that tells us is that our domain then. So if you think about it, you cannot plug in the vertical asymptote. By the way, we end up calling that VA for short. Vertical asymptote, VA. So if your VA is the value that you cannot plug in because it's an error, well then what can you plug in? Look back up at those tables. You can't plug in 2, but what can you plug in? It's like everything other than 2. As long as it's not 2, you get an answer. Look over here. What's the domain for this one then? You can't plug in negative 3 because that's your error, that's your vertical asymptote. Okay, well then what can you plug in? You can plug in everything except for -3. So as far as the domain goes for these, it's pretty much all real numbers, but with a giant caveat, except. So it's everything except the vertical asymptote. And I'm going to show you how to write that on my next screen. So you will come back and take a little bit more notes. But as far as just the vocabulary goes, the domain for these is that you can pretty much plug in whatever you want with the exception of the error. Okay, so now I'm going to transition. Oh, that's my face again. Hi. Now I'm going to transition to the whiteboard feature of this so that you can kind of see some of this a little bit more in action. Oh, let me clear that. There we go. Clear. All right. So let's say that we had a function. So now I'm just going to try to make things generic. So if we had a function that said, 2x over 3x minus 5. And obviously you could graph this in Desmos, so no worries there. Sometimes you have to put a parentheses on top and also a parentheses on the bottom so that Desmos knows what's on top and what's on bottom. But you can obviously graph it and you'll get a nice picture of what it looks like. But then my question to you, of course, is going to be, where is the vertical asymptote for this formula? Where is the error? Where is the division by 0? And you're looking at this one and you're like, well, oh my gosh, I don't know. 3 times what? -5 makes 0? I don't know. And the thing is you don't have to know in your head. What you just have to be able to do is the algebra. So 3x minus 5, what number would make that 0? You can't do it in your head? That's okay, neither can I. But can we use algebra? Yes, we can. So in this case, when does 3x minus 5 equal 0? Well, it would happen at 5/3, aka 1.6 repeating. No, yes, 1.6. Sorry. So 1 2/3 essentially. So this right here would be the vertical asymptote for that graph. And if you look on graph paper, I'm willing to bet good money that you'll notice the graph, quote, breaks apart at just about 1.5. Okay, but don't eyeball it. Please don't say that the vertical asymptote is at about 1.5. No, it's at 5/3. Do the algebra. So since we now know that the vertical asymptote is at 5/3, the vertical asymptote is at x equals 5/3. What that then tells me is that my domain is everything except, check it out. That's how you can say except, just an equal to bar with the line going through it. And that's the mathematical way of saying except 5/3. So that's kind of how you piece it all together, so to speak, where if I give you a rational function, and obviously you can graph it using Desmos, but if I say, okay, well, what's the VA? What's the vertical asymptote? If you can do it in your head, cool. But if not, it just comes from that denominator and asking yourself when that denominator would be 0. So now if we go back to our document, let's see, back to our document, here we go. Okay, so back here, for vertical asymptote, we already wrote down the value of the input that causes an error. So I want you to go back to that little section of your notes and just make a little asterisk that you can set the denominator equal to 0 and solve. Okay, that's how you'll know where that comes from. So if you go back up here, 2x plus 6 equals 0. Just imagine for a second, 2x plus 6 equals 0. If you had to do that in your head, I'm sorry, if you couldn't do that in your head, 2x plus 6, huh? So 2x plus 6 equals 0. Sure enough, couple of steps of algebra, and you would absolutely see that the vertical asymptote is at x equals -3. Vertical asymptote is at x equals -3, which then tells me that the domain for that graph was everything except -3. What can I plug in? I can plug in whatever the heck I want except -3. Because if you do plug in -3, you get an error. That's not cool. The graph does not exist at that point. And so it becomes very important for you to be able to identify where that is. And so as we wrap up this video, you've got some vocabulary. I need you to have taken notes, obviously, on that. And the expectation when you graph these, once again, is that you've got your dotted line drawn in for your vertical asymptote, and then you can draw those two branches, but just be really careful when you draw those two branches, guys, because you cannot just go slicing through the vertical asymptote. We draw the dotted line there for a reason. It essentially guides your pencil to not accidentally cross over that boundary line. All right. Okay, hopefully that made sense. The next video will talk us through horizontal asymptotes, because yes, there's horizontal asymptotes as well. Go figure. That's the next video. Hopefully this one made sense. If not, reach out to me, come to my office hours, and we'll talk to you guys soon. Thank you.